Hello and welcome to the Daily Space for today, May 14th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Today, we will be joined by the Planetary Science Institute's own Katherine Johnson, one of the researchers of a recent study to look at Mars' magnetic field. Using Mars Maven data, this team found indications that Mars magnetic activity, occurred as recently as 3.7 billion years ago. Dr. Johnson's work addresses a myriad of global data sets that allow her to probe the internal structure of worlds while living right here on Earth. Remote sensing is an awesome thing. But before we get to that interview, let's take a look at the news. Today's top story looks at an area of astronomy that rarely makes headlines. I'm talking about pulsating variable stars. As some of you may know, I actually started my career first looking at T Tauri variable stars in the radio, and then moving on to study Cepheids and Aurolaries using optical telescopes. Now, I switched to extragalactic in graduate school after being told that stars, pulsating stars in particular, are pretty much a solved problem. Here's the thing. Stars have long been underappreciated, underfunded, and folks often fail to realize just how complex stars can be because they're kind of plain Jane on the outside. They're just big old glowing spheres. But as more and more researchers have had to look at stars while they're trying to find planets, stars are getting a lot more attention as folks recognize these really are super complex objects that behave in a lot of ways that aren't solved, and we still have a lot to understand. Now, variable stars come in lots of kinds. Some flare up randomly, some darken suddenly. Pulsating variable stars are stars that have just the right balance of gravity pushing in, temperature, and energy generation on the inside, that as light pushes outwards, it sometimes gets stolen by the star's outer atmosphere. And instead of radiating out, it essentially gets trapped and pressure builds up until the star suddenly expands back out. It's not always that sudden. Expands back out. And as it expands, it cools, that light is released, and the star collapses back down. And this cycle just goes on over and over again. These changes in brightness and color for many stars can be seen just by standing in your driveway on a darkish night and looking up at just the right objects. This can be seen without telescopes or binoculars. You can just look up and see these stars changing hour upon hour. Now, one of the favorite kinds of objects for people who do this as a hobby are delta Scuti variable stars. These young stars are just a couple of times the size of the sun. And if you try and make a plot of their brightness over time, it's super chaotic. And these changes reflect that these stars are both rotating rapidly and also pulsating in ways that we haven't been able to understand, at least until now. Astronomers using TESS and Kepler, two telescopes designed to take image after image to search for extrasolar planets, astronomers using these planets to instead study the stars and combining that data with ground-based observations with Las Cumbres Observatory, they've discovered that there are two different classes of delta Scuti variable stars that we actually can understand if we just take into account all the right variables. One set of these stars behaves in a way that kind of makes sense to our gut. These stars are completely pulsating in and out in a nice symmetric way while rapidly rotating. Now, the other set of stars is a little bit more confusing and I believe will be captured in this video. So here we're seeing a nice symmetric pulsation taking place. Stars rotating, and you can see how the rotating can make chaos. Now, instead of symmetrically pulsing, what you're seeing here is different quadrants of the star or different hemispheres of the star rotating at different times. That's right. Stars can pulsate in quadrants. They can actually pulsate in much higher orders of nodes, dividing them up into checkered systems where the black parts of the checkers are doing one thing while the white do another. These are oscillating bubbles of plasma. And these oscillations allow us to understand the inside of a star. Now, what makes these particular stars, the Delta Scuti, so complex is to try and understand them, we have to decouple what parts of the star are actively pulsating. And if the star is rapidly rotating, those parts are going to be rotating in and out of our field of view in rapid fire. So this is one of those complicated issues. And the team that actually started to solve this problem, a team led by Tim Betting, has just published a paper in the journal Nature that shows that while ridiculously hard to understand means a whole lot of work needs to be done, it also means the work can be done, the problem can be solved. And with the solutions they've come up with, we can now start to use the detected pulsations to map out the insides of these stars the same way we use seismic waves to map out the insides of planets. These new findings are already allowing researchers to use pulsating young objects, pulsating Delta Scuti stars to determine the age of their surroundings, including using one of these stars to determine that there is a stream of young stars orbiting our own Milky Way galaxy. Pressures of all kinds don't just drive pulsating variables. They affect all the different kinds of things that we see out there in our sky. Stars pulsate under pressure. Galaxies echo as light bounces around the inside of a galaxy. And even small moons can erupt when their internal pressure gets too great. We know from clear images of the moon Enceladus that were taken by the Cassini mission that at least this icy moon has geysers driven by the tidal effects of Saturn. But while this tidally tortured moon has made it clear that yes, it is erupting, Europa has been a little bit harder to sort out. The question has been, do we have enough evidence to say with certainty that Europa does have geysers? We have seen hints of what look like they could be geysers in Hubble data, but we don't have the resolution to say it with certainty. And we have data from Galileo that can be interpreted as geysers being picked up in some of the magnetic field data. But it's been nothing definite. And we still don't have anything I'd label as definitive. But we do have more computer models saying that, yeah, there probably needs to be geysers to explain some of the data that we're seeing. Looking at data from Galileo's energetic particles detector, this is this is an instrument that detects, high energy particles streaming through the system. They have found a section of data that was acquired at the same time that magnetic data seemed to indicate they flew the spacecraft through a geyser plume. And a team led by Hans Heibrigs found that in the energetic particles detector, they didn't detect as many protons as they expected. And the only way that seemed obvious to explain this data with their models is to say, yes, there's a geyser. Now, so far, nothing else fits this particular gap. Nothing else fits the magnetic data. But what we're actually doing is trying to figure out if there's a geyser by looking at a shadow in the data. And we're not going to be able to say for certain, probably, whether or not there's a geyser until the Europa clipper gets there. But this is tantalizing, and this shows how every different instrument we put on a spacecraft can be repurposed to do science we never imagined. Unfortunately, Juno doesn't have any instruments that we've figured out how to repurpose to figure out if Europa has geysers, and it's in entirely the wrong orbit, so that's not going to happen. So stop hoping that Juno is going to say geysers. But this is still a really cool way to use really old data to figure out really cool new science. Now, the distances to these interesting worlds can be hugely frustrating. It takes years, sometimes decades, for our missions to get where we want them to go to study the objects that we're still learning about. And the brief time that the spacecraft get to spend at those objects is also hugely frustrating. At Jupiter, Galileo gave us years and gigabytes of information. At Pluto, New Horizons just had moments. But sometimes moments are just enough to get the right information to start something awesome. New Horizons looked back at Pluto, and as it looked back, it saw sunlight streaming through a haze, a thin layered atmosphere. And this gave us information on what the actual atmosphere of Pluto is and put limits on our understanding of how the surface of Pluto is turning into an atmosphere and the collapsing back down to the surface of Pluto. Now, we only had this one chance with New Horizons to get this one set of images as New Horizons left this system. But now, Earthbound observers have taken to the sky with the SOFIA Airborne Observatory to take advantage of special moments in Pluto's orbit when, from the perspective of us here on Earth, Pluto passes directly in front of a distant star. Now, in these moments when Pluto passes in front of the star, that starlight can be seen shining through Pluto's atmosphere, giving us additional opportunities to study Pluto's haze. And now researchers who've been doing this work have published a new paper in the journal Icarus that is saying the reason that this haze continues to linger longer than we ever expected, and this was one of New Horizons' awesome findings. They didn't know how much atmosphere they'd see, and they saw a whole lot more than they expected. And now SOFIA, which is let out of the SETI Institute, is able to say, not let out of the SETI Institute, this team was let out of the SETI Institute, so sorry. They're able to say that the reason this haze is able to linger is it's much smaller than we previously thought. And these tiny, tiny particles, once lofted, take longer to settle back down. This is something a lot of us have experienced before. You toss a bunch of gravel up, it's just going to come straight back down. You clap chalkboard erasers and that fine particulate stays suspended. Well, this haze is essentially a suspended atmosphere that takes time to settle back down. Now, unfortunately, unlike the haze, we can't linger at Pluto. We have an interview to get to. In just a moment, I am going to bring on Dr. Katherine Johnson, and we're going to continue our explorations of the solar system as we turn to Mars and the recent work that the team she's part of has done using Maven data to, well, start to figure out When did Mars have an active magnetic field? The kind of magnetic field that just might have made it a little bit easier for an atmosphere and all the things an atmosphere allows to have existed on Mars. Now, I am going to put up the Be Right Back video, and I promise you, this time I'm not going to blast your ears with the volume. Apologies for times when I've blasted you before. So I'm going to put up this video and then come right back with Dr. Johnson. So please don't go anywhere. The science will continue. Hello, everyone, and welcome back. I am now joined with Dr. Katherine Johnson, someone I am proud to share the Planetary Science Institute label with, and she also is at the University of British Columbia, which is oddly where my husband went to university. So it's a very small world, and welcome to our show. How are you doing today?
Thank you. Very well.
Now, we highlighted your recent research paper a couple of weeks ago here on the show, and I'd love it though if we could hear about it in your own words. What did you do to, well, probe Mars' magnetic field?
Sure. Well, as you know, Mars doesn't have a magnetic field today. It doesn't have a global magnetic field like we do on the Earth. But in the late 1990s, the Mars Global Surveyor spacecraft was in orbit around Mars. And that spacecraft, during its early aerobraking phase, when it was coming in and using Mars's atmosphere to bring it into a more circular orbit, that spacecraft actually detected little signals of magnetic fields. And as people put the picture together from Mars Global Surveyor, what they saw was that there were magnetic fields over some parts of the planet, but not others, and much weaker than the Earth's field, and clearly sort of associated with some geological regions. And so the big conclusion from that was that some of the rocks on Mars are magnetized today. They hold magnetization today. They're like little permanent magnets. And the way that they got magnetized was in an ancient magnetic field. But one of the big questions has always been, we know that this field was ancient, but how ancient? Was it done by the time there were big impacts on the surface that created these basins, or did it come afterwards? And both ideas have been around for a while. And so what we did was we went back and looked at some more recent data from the Maven spacecraft, which is now in orbit around Mars. So Mars Global Surveyor is no longer in orbit around Mars. Then there was a hiatus for over a decade. And then Maven has been in orbit around Mars since 2014. And it has some parts of its orbit that fly closer to the surface of the planet than Mars Global Surveyor did. Still a long way away, still over 100 kilometers away. But we used some of these data to try to really address this question of when did the magnetic field on Mars actually, when was it present, and when did it switch off? And go ahead.
And magnetic fields, we often talk about them and how important they are for protecting the atmosphere of the world, allowing basically the sun's wind to get more deflected and not having those high impact charged particles slowly stripping away the atmosphere. But that magnetic field is the side effect of Mars still being liquidy on the inside. And so this also gets at cooling rates. Now, can you give us some insights on what the magnetic field tells us about the inside of the world?
Right. So if you have a magnetic field at some point in a planet's history, so now we're talking about a global field, not the field that Mars has today from these magnetized rocks. So the field that it had when the rocks became magnetized. If a planet has a field like that, with a North Pole and a South Pole, magnetic pole, like we do on the Earth, it tells you that that planet, if it's a rocky planet like Mars or Venus or the Earth, the Moon, Mercury, it tells you that that deep interior of that planet that we know is made of metal, that's still liquid and moving around quickly enough that it can generate a magnetic field. So it's liquid metal, which is a conductor. And so as that conductor moves around, it generates a magnetic field. And for that to happen, the planet has to be cooling relatively rapidly. And so for many planets, this only happens early in their history, particularly for smaller planets. We think this is true, although pretty much in our solar system, every planet is a puzzle in that regard. Mercury small still has a feel. What we found for Mars was that with the Maven data is that there was evidence for a magnetic field. We found sort of two tie points, one much earlier than people had thought previously, right at the very beginnings of Mars's history. We think it had a magnetic field. And then one tie point where we found rocks that are younger than people thought was typical of the magnetic field persisting. Those are about still old for us, 3.7 billion years old, but suggests that Mars had a magnetic field then. And this ties to your comment about atmospheres, right? Previously, people thought that Mars's global magnetic field switched off probably before the big basins formed, and most of those formed before the evidence for liquid water and an atmosphere on the surface. And so this question of what did the magnetic field and the atmosphere know about each other? Did they have anything to do with each other when one was present and the other was not? Previously, it seemed like the atmosphere just came after the magnetic field, this thicker atmosphere. What our results show is that actually there was a magnetic field present at least after these big evidences for water on the surface of Mars. And so this is really interesting because it opens up this question again as, was there a magnetic field there that was helping protect Mars's atmosphere? How much those magnetic fields are needed to protect an atmosphere is a huge open question in planetary science.
So let's try and unpack a lot of this because there's so much cool stuff going on. So pretty much early in our solar system, everything was a giant pile of goo or gas surrounding a pile of goo. So we had a liquid core to Mercury, a liquid core to Earth. We still got it. And Mars early on was a hotter world. It had that liquid metallic core. It was generating a magnetic field. And then over time, like a bunch of different pastries set on the counter, things cooled at different rates depending on their composition and their size. So just like a big old hot pudding will take longer to cool than a little tiny dried out muffin, well, Earth, we're still hot, and Mars, well, we don't know Mars well enough to know exactly when it cooled, but we know it cooled before us. Now, not all rocks formed on a world capture magnetic fields. Is that a fair assessment?
That's right. So I saw some interesting things on the chat actually.
Yeah.
So about the cooling, right? So in general, smaller planets, even if they have the same amount of, there's a great question here about radioactivity. Is Mars cooler today because it has less radioactivity? And the answer is probably not that. Smaller planets cool more quickly because they have more surface area relative to their volume, right? So they'll tend to cool more quickly. So in general, everything else being equal, and if cooling is the only thing that makes a magnetic field, global magnetic field, then they'll tend to have cooled more quickly, perhaps switched off their magnetic field earlier. But there's another thing that helps you have a magnetic field, and that's as a planet cools, that liquid core solidifies. And when it solidifies, so just like it takes energy to melt something, when something cools and solidifies, it releases energy. And so the solidification of that core from the inside out actually can help you drive a dynamo because it's releasing heat, and it also releases a little bit of, it's not exactly, the liquid core isn't exactly pure iron, it's got some light stuff, and when it freezes, the light stuff is concentrated in the liquid. So there are ways to kind of help this evolution through time. And then what you see on the surface today, your question was about not all rocks record magnetic fields. So what you see today is basically the record of what rocks formed during the period that you had a magnetic field, and were those rocks, did they have iron minerals in them, right? So different compositions of rocks will be different recorders of the same field. And so these are the things that when we look at satellite data and we try to decide, does this area have magnetic fields on the surface of Mars? Does this area not? Or it does, but it's different. Is it different because the rocks are different? Or is it different because the surfaces are a different age and recording a different time? And so we try to disentangle all of these things.
And so there's this complicated struggle of trying to figure out if this particular geological region that we're looking at, and we can figure out how old this region is versus that region by counting craters, because more or less the universe is throwing rocks at Mars at a known rate ish. And so you look and you count how many craters are in one place, you count how many craters are in another place, you accept the fact that wind is eroding things, which is confusing, and you more or less know this is older than this. And when you look at one region and you do or you don't find a magnetic field, you ask yourself, is it because the rocks aren't any good for solving this problem? Or is it because the magnetic field turned off? So you have to look at lots and lots of regions that are the same age to try and figure this out.
Yep, that's right. And then there's like even one more kind of complication to this. And this is where our study came in, which is you can identify regions that have magnetic fields or magnetized rocks, and you know something about their ages, but you know about the age of the surface.
Yes.
And the rocks that are magnetized might be near the surface, or they might be quite deep beneath the surface. So for any of you who've been to like Hawaii or anywhere with big like cliffs and layers of rocks, the rocks at the top will be a very different age often from the ones at the bottom. And so if all I know is the age of the one at the top, but the one at the bottom is the one that's magnetized, right? Then my conclusions can be wrong because I put the wrong age with that rock. And so one of the things that we did in this study was we were able to find a place where we know it's the rocks that are near the surface that are magnetized.
How do you know that?
And the reason that we know that is it's a big lava flow. And you can see that the magnetic field signal is in the same place that the lava flow is. That still doesn't tell you exactly. It still could be just fortuitous and beneath the surface. But what we see is in the middle of that lava flow, there's a very, very young, fresh crater. And we know that crater is so fresh that it's unlikely that the magnetic field was on when that crater formed. Nobody would think Mars had a magnetic field that long because we don't see it over any other really, really young terrain like that. So that crater is very young, and it's punched a hole to the bottom of that lava flow. In fact, we can see that it goes all the way through to the bottom, like a kilometer or so, just actually more like a mile, to the bottom of this big set of lava flows. And associated with that crater is basically a dip in the magnetic field, a big dip, almost like completely gone over this crater. And so we basically know that this lava flow is magnetized, is correlated, the magnetization is correlated with the flow, and there's a hole in the middle of it where this crater is present. So we can say that it's almost certainly that set of flows that are near the surface whose age we know versus being something much deeper.
And that is just one of those lucky finds. And I have to ask, how did you guys realize this one crater on this entire world is the key to figuring this out? do you know within the team who it was that initially discovered this young crater?
So this was the work of my postdoc, who's the
Uh-huh.
first author on this paper, and myself. And the way we went about it was we basically looked at Maven data, and we said, where are there signals in Maven data that we didn't see them in Mars Global Surveyor already?
Yeah.
And so that takes out a big part of the planet, because a big part of the planet we knew about. And then we said, let's look for places where we know that there are flows whose age we know, or volcanoes, but flows are a little easier to talk about for reasons that are just kind of complicated and boring. But so we looked for regions that would be interesting in terms of being younger than people had thought about the magnet. Many people had thought about the magnetic field before, and where we already saw new signals. And then we looked at everything, just like when you do weeding in your garden.
Yeah.
You gradually go through everywhere, right? And along the way, maybe there's a plant that you didn't know was there and isn't a weed, right? So we looked.
And that's the thing about science that our community largely discovered while helping the OSIRIS-REx team map out Bennu. A whole lot of science is systematically looking at a whole lot of things that look absolutely identical, or at least variations on a single boring theme. But as you look, you'll eventually find that one thing that makes all the difference in how you understand a world. Now, with what you guys did, one of the things that I picked up in the research paper was there's other regions that had been dated as being slightly older and didn't seem to have magnetic fields. Can you talk about this a little bit? What is this telling us?
Right. So we found, this one evidence for very ancient, right at the beginning of Mars's history, as you said, very ancient fields. And then other people, the big results from Mars Global Surveyor showed that there was a magnetic field after that even. So we have the earliest one, then this time period from about 4.3 to 4.1 billion years ago. And then the argument has always been that when you look at craters, big impact basins, in particular, sort of 2 or 3 of them over the surface of the planet of Mars, they don't have magnetic fields in their interior. And their ages are all in the sort of 3.9-ish billion years ago. And then we have this time after that, this young flow, where we see. So the interpretation has always been that those big impact basins formed when Mars didn't have a global field. When an impactor hits the surface, everything inside the basin is ejected and melted. And then as it cooled back down again, if there was a magnetic field, a global field, the argument is always that those rocks would record the global field. So the absence of a magnetic field over those basins was taken as meaning that they formed when there was no global field, because the rocks cooled in the absence of a field, so they're not magnetized. And so the question is, how can you have this time before and the time after and nothing in between? Magnetic fields can switch on and off, so that's one possibility, but it has to be very fortuitous, just timed exactly right with the basins. So one of the things that we suggest in this paper is really based on our knowledge from the Earth, and also what we discovered in the paper, which is that much of the magnetization is carried in rocks in the crust, what we call the crust of the Earth. So sort of the top 10 to 5 to 50 kilometers. When these big basins formed, they make holes that are that deep. So they basically can remove almost all of the crust in that region. On the Earth, the rocks that lie beneath the crust in the mantle, those are actually much, much less magnetic. And we have meteorites from Mars that have compositions of sort of Martian crust and also compositions that we think are Martian mantle-like. The ones that are more mantle-like are much less magnetic.
And this is a composition difference. This
Yeah.
isn't a
So
I
then
will
this
be, I
would
won't
be
be. It's just they're made of different
so it
stuff.
could just be that when you make these basins, you remove all the stuff that can be magnetized. And you still have a magnetic field present, but the rocks that are left, the ones that are typically deeper, that those can't be magnetized, or they're magnetized so weakly that even at these satellite altitudes, we can't see it. So we could test this by flying much closer to the surface with helicopters or planes or balloons, right? That would be a way to test it.
And I don't think that Perseverance's little helicopter is going to be able to give us this information, but we can dream of future missions. But for now, this is allowing us to start to develop a tantalizing timeline for the red planet, where we're looking at how does the magnetic field's presence or lack thereof compare with that time when during and after the great heavy bombardment, there was liquid carried to Mars, just like there was liquid carried to Earth. And Mars, like Earth, had oceans. And not like Earth, its atmosphere was much smaller and sadder. Probably not sad, it lacked emotions, but much smaller. Um, if that magnetic field was there at the same time, how does that change how we model the atmosphere that could have been there?
Right. So if Mars had so you're talking about if there was a magnetic field present
Yeah.
at the time there was an atmosphere,
Yeah.
right? This is actually one of the things that people have been looking at, both with Maven data. One of the big, actually, the big objective of the Maven mission is to understand how Mars is losing its atmosphere today.
Yeah.
Right? What are the rates? Where does the atmosphere escape? How fast, under what conditions? To try to actually understand, even just today, to go back in time. But then, of course, if you go back in time, we don't have measurements of atmospheric loss directly, right? So one of the ways we can look at that is through numerical models. And people have actually, quite recently, there was a paper where people looked at numerical simulations of atmospheric loss on Mars with a magnetic field, and then seeing a global field, and then seeing, as you decrease the strength of that global field, at what point does the atmosphere start being lost, right? So there are sort of different ways that people go about trying to understand this, but one of the things that I think clear is that strong global magnetic fields do help. Whether they're required to protect an atmosphere is a different question, but they certainly help. And so if you had an atmosphere present during this period of water on the surface, it certainly would help keep that atmosphere there for a little bit longer. I mean, it's just a huge set of questions for Mars is, why did it have this different climate, and how was the atmosphere then lost, right?
And so this starts to become more a case, it sounds like, of time scales where, sure, it can have an atmosphere and not have a magnetic field, but if the magnetic field is present, it slows the erosion process of that atmosphere.
Right. As long as that magnetic field is strong enough, sufficiently strong. It turns out what people are starting to learn is, in some of these simulations, if the planet has a magnetic field, a global one, but it's actually quite weak, much weaker than the Earth's today, then in fact, the presence of the weak field can facilitate atmospheric loss. So it's all sorts of things that we don't know, but certainly a strong field, which is what we think Mars probably had at the time it had one. Our work suggests it would have been Earth-like from the magnetizations of the rocks. That would definitely help.
So is there a name for this phenomenon the atmosphere is asking of the magnetic field and the atmosphere interplaying to protect or, it appears, accelerate the loss of atmosphere?
No, it's a great question. I see that question on the chat. Is there a name for the loss of the atmosphere due to the loss of the magnetic field? Does something limit? No, we don't have a name for it because we really don't understand the details of it well enough, right? How strong is it? Just the strength of the field overall. If you turn it down below a certain number, do you lose an atmosphere? Or more likely, it's probably related to a combination, the balance of the strength of the magnetic field and how thick the atmosphere is, because an atmosphere helps protect itself. Venus is a great example, right? So, so we don't have names for it because we're still figuring out the physical mechanism.
See, this is how planetary scientists differ from us astronomers, because the second we discover something we don't understand, that's when we name it. So, I appreciate that difference. Now, we've had a bunch of questions that I have to admit I haven't thought about with Mars. So here on Earth, we see, particularly in the mid-ocean trenches, the rocks show flipping magnetic fields over time.
Mhm.
Do we have the capacity to look for similar polarity changes on Mars?
It's very difficult to see that from orbit.
Okay.
From a satellite, from satellite orbits. If all we had on the Earth was satellite data,
Yeah.
we know this, right? We know it because we were able to get much closer to the surface. The definitive way to know that is to have rock samples from the surface.
Uh-huh.
The definitive way to know about timing is to have rock samples from the surface that you can measure in the lab on the Earth. You have to do it. You can't really do it in situ with a
Yeah.
rover, because you need to actually be able to do some experiments to be sure that that magnetization is an ancient one, and then to get an age of that rock. This is what we do on the Earth, right? We take samples, we go to places like Hawaii and take drill cores. We
Yeah.
know which ways the rocks are oriented, and then we can measure their magnetization in the lab. We measure their age, and we know how the rock was oriented, and that the cliff section isn't all collapsed, or
Right, right.
so we know that that's in, we call it in place. um, and so then we can see, is the direction flipping. So that's really the best way. We can do a little bit better than that. We could get some ideas of that with being just closer to the surface, but the definitive record comes from actually looking at rocks and
And
measuring rocks.
and this isn't a matter of we have to have humans on Mars. It's an issue of we need to be able to expend a whole lot more energy than our little tiny happy rovers are able to do. Our rovers just don't have the uh, basically the wattage to drill core samples. And since they don't have the wattage, we don't even bother to build the instrumentation. It takes a lot of machinery to drill the samples. And then, of course, the labs that we use take up a whole lot more space than what fits on our rovers. So we could do it robotically. The oil companies have a lot of tech we could steal, but we can't do it with the size and the size restrictions of our current rovers and the energy restrictions of our current rovers. But humans would be nice. Humans would be nice. Um, Now, in looking at Mars, when you are finding these vestigial um, magnetic fields, you mentioned finding it in a lava flow. Um, what other kinds of places do we look, and what does that tell us about the internal structures that were spitting out this can form natural magnets material that was coming out onto the surface?
We look at rocks in different places, right? With different, where we think, maybe based on what we see from spectroscopic data from satellites, which tells us something about composition, where we think rocks might have different compositions. So we try to look at the record of ancient magnetism in different places to try to understand something about at least the iron composition of the rock. One of the things that we were able to do in this study, which was really helpful, was because, you know, that little crater is really key to the whole story. That little crater, because it penetrates to the bottom of this lava flow,
right?
We know how thick the layer is that carries the magnetization. And so when we measure a magnetic field over this layer, all you know is basically about the combined effects of the thickness of the layer, what kinds of minerals, how strong the magnetic minerals are, and how much of them is present, right? And by knowing the thickness of that layer, we've taken out one of those variables, right? So now we can say we get this magnetic field, we know what the thickness of the layer is. So the two things that we don't know, that are just trading off with each other, are what is the magnetic mineralogy, how magnetizable is this rock, and how much magnetizable stuff is there. But because we know even the combination of those two things, we can compare that number that combines those two things with the same number, the magnetization of rocks on the Earth, of rocks with what we think might be similar compositions. So this lava flow is what we call a pyroclastic basaltic lava flow. So we know something, the basalt is something about its composition, and the pyroclastic is something about the way in which it was erupted. So we can compare that magnetization with similar rocks on the Earth. And in fact, it's very similar to many of the rocks that we see on the Earth. And so we can start to say more about the mineralogy, at least in that place. It may well be like some of the pyroclastic basaltic lava flows that we see on the Earth. And furthermore, because it's like that, very much like that, then probably the strength of the field in which that rock was magnetized was similar to that of the Earth today.
So I just want to pause for a moment. Pyroclastic basaltic lava flow.
Yes.
I understood the last two words, and because I've gone to a whole lot of LPFCs, I understood the first few, but I'm not sure everyone did. Can you break that down?
Right. So I was trying to get there a little bit in terms of the first one. Pyroclastic actually usually refers to very violent eruption.
Yeah.
One that would have erupted, kind of a mix of lava flow material, what we call actually bombs, just big blocks of rocks, ash. It can be ash.
Was this the recent tragic New Zealand eruption?
Yes, that's a pyroclastic.
Yeah.
Pyroclastic flows. And so the pyroclastic is about basically the type of eruption that's happening. The basaltic inference comes from spectroscopic work, other people's work over the area.
Composition.
That's the composition part. And basalts are basically, by basaltic, we mean something like you would see in Hawaii, in the cliffs in Hawaii, like you would see in the Snake River Plain. These kinds of magnetic mineralogies that you see in big lava flows on the Earth. And in those big lava flows on the Earth, we know what kinds of iron minerals are present. So it helps us with understanding the iron mineralogy, at least in that place on Mars.
Now, the magnetic fields that you're talking about here, we're all of us generally used to the magnets that we stick on our refrigerator, the magnets that we encounter if we take apart speakers. But if I go to Hawaii and I start picking up lava rock, I can't stick it to the front of my refrigerator.
Right.
So how strong does the magnetic field need to be for you to be able to detect it? Are you talking about super tiny magnetic fields?
They're really quite small. So by comparison, if you were to just take an instrument that measures the magnetic field strength on the Earth, if you were, I'm in San Diego, and if you were to take it outside in San Diego or low latitudes on the Earth, it would measure a magnetic field that's somewhere between 30 and 40,000 nanoteslas. That's our units.
Okay.
use here. Most of that is about the global field of the Earth. So if you were to do the same thing in Hawaii, you get some similar number. If you were to subtract the global field, the leftover signal would be a few hundred to a few thousand nanoteslas. So it's a few percent to 10% of the global field. That's the field from the rocks themselves, right? If you and so if you were to look on Mars, the strongest place, the flow that we looked at, it would be similar on Mars. Some other places in the southern hemisphere have magnetic fields from the rocks that are much stronger than on the Earth, maybe 10 times stronger. But we don't yet know whether that's because there's just more magnetizable stuff there, or because the magnetization itself is stronger, right? Is it a rock layer that's sort of the same thickness as on the Earth typically, but more strongly magnetized, or is there more?
And
this has been a question for us in understanding.
And this is exactly what I wanted to get at, is we don't know if on Mars the individual magnetic field preserving rocks are those Hawaii-like lava rocks that you absolutely cannot stick on your refrigerator, or are they more like the naturally occurring magnetic rocks that people buy to put in their sewing kits to pick up needles? And it's the en masse effect of having so much of this material that allows Maven to detect things. Is this accurate? It's everything added up that creates the magnetic field?
Yeah, that's right. It could be just like on the Earth, just like Hawaii type flows, and there's more of it in the places where the magnetizations are stronger. There's more of it, or it could be rocks that in some places are quite different, like you described. What enables Maven, or in the past Mars Global Surveyor, to see those magnetic fields is that they're strong enough, but they also exist over are present over a big enough spatial area. So even if they were sort of Hawaii-like, or even 10 times stronger than Hawaii, but they only exist in a patch that's the size of, well, anybody who lives in a city, their backyard, maybe not people in the countryside with acres and acres. But if it's a very small area, then you won't see it because you're too far away.
Yeah.
And so it's the combination of having something that is fairly strong anyway, at least Earth-like in terms of the rocks, but that there are big areas that are actually magnetized.
And it's really all of these different things. This is effectively the reason we learned calculus, is to integrate over the volume of the magnetic field generating material.
That's right.
now,
and also to be able to solve, to look at our bank accounts.
Well, if you're using calculus to do your bank account, I'm glad I don't have your bank account. Mine, luckily, I can handle with Excel. Not that I do. I handle it with Google Slides because I'm cheap. But going back to magnetic fields, Hanny's looking at the very early moments of when this might have all started. Does the planet have to have hit the point where it started to differentiate in the cooling blob before you get the magnetic field?
Yeah, that's a great question. Traditionally, that's been our thinking. I think there are people starting to think about, could you have a magnetic field present when the planet hadn't differentiated, so hadn't separated the metal part, hadn't fallen towards the center to form a metal core. So if you have a planet that is, this sort of mixture of molten, not molten rock and metal all together, could you actually generate a magnetic field in that? It's more difficult because one of the things that having just a differentiated planet and a metal core helps with is that metal is all in the same place, and it can move in a way that's it can flow in this big relatively big volume,
Yeah.
right? And it's the large scale flow that's set up that gives you a large scale global field. So it might be that planets had magnetic fields even before they had fully differentiated. It's a great question to bring up. But I think, all of our current understanding is really about planets that have already differentiated and
A-
their fields.
And the frustration is that the surface of worlds from those blobby molten days doesn't still hang around to preserve a record of those days.
Right.
So we're just going to have to try and model our way all the way back to the past as we live in the now. And it's so frustrating, but this is why we do science, to try and figure these things out. Now, we have been going for 45 minutes or so, and this has been tremendous. And I could keep you here, but I'm sure that you have science you need to go off and be doing. So, do you have any parting words, anything that you really just want to make sure everyone here understands about what we're learning today about Mars?
I think for me, the exciting thing for Mars,
Yeah.
from a Mars perspective, is just this idea that you could have had a magnetic field present when there was a different atmosphere. For me, just as a scientist and a person who's involved in education, uh, the thing I think is the take home point is just never ignore that little thing that you see that makes you say, that's really weird. I wonder why that's there, because it might have a story.
And I just love how this story rests on one postdoc finding one crater in one particularly magnetized volcanic lava flow. It's it's a fabulous story. Now, if people want to follow your work, are there any particular missions or places they should be looking?
Yes, I worked for several years on the Messenger mission to Mercury. So lots and lots of fun stuff. I'm still a big fan of, I call it the little hot one.
Yes, yes.
um, so the Messenger mission, a really amazing mission. The Bepi Colombo mission, of course, is on its way to Mercury. I'm also
2027, 2025.
2027
That's what
arrival.
I, yeah.
Well, it depends whether you count flybys or arrival, but it's a little ways away. But yes, the Bepi Colombo mission, which will be amazing. Lots of good thoughts and plans for future missions to Mercury. And then I'm also involved in the Osiris Rex mission to Bennu.
I think we have a collective, we hate rocks due to that little world. And I'm glad that you're here to love it with us.
Yeah.
And this is just a reminder that planetary science is the long game. Bepi Colombo was named in 1999. That's 28 years from naming to orbiting. And we play the long game because, well, our long game is still really short in the time span of the universe. This has been awesome. Can we bring you back next time you have new
Very lovely.
findings?
Love.
Okay. So thank you so much. I'm gonna let you run away and go back to a picture of Pluto haze. Thank you so much, and we will invite you back. You don't need to stay while I say the credits. So thank you, audience. This has been the Daily Space. You can learn more about Katherine's research on the Planetary Science Institute website, and we, like her, are part of the Planetary Science Institute. The Daily Space today was written by me, Dr. Pamela Gay. The audio will be produced by Ali Pelfrey. The video will be produced by Tim Hawkins. The content will be, well, put all the places you can go to find it on Patreon, our website, and Instagram by Beth Johnson. Our team is supported through a fleet of volunteers. Thank you, Bad Panda, for the sub. And it's through your help, through your bits, through your patronage that we're able to do everything we do. Thank you so much. If you'd like to support our show, the best thing you can do is join us at patreon.com/CosmoQuestX. Now, it's plague times, and we know a lot of you are struggling. And if you can't give, That's totally cool. Come join us. Come science with us. Come help us do all the things we do. Together, we can get through plague times and make everything a little bit more scientific in the process. So find out what's going on. Everything is linked to cosmoquest.org. So I am now going to look for somebody to raid. If you have any thoughts or ideas, please let me know where you would like to go. This is me looking to see what all is going on at the moment. How about Oh Bother or EJ? Do you have any preferences? Actually, we haven't rated Oh Bother this week. Let's rate Oh Bother this week. So thank you all for being here, and wherever you are, have a fabulous morning, evening, or afternoon. Remember, wear a mask if you go outside, wash your hands a lot, and if you can, just shelter in place. And we're going to get through all of this together. Bye-bye, everyone.